Today I will be talking about automated REST API vulnerability detection, specifically with the tool we developed, WuppieFuzz, a fully open source tool. But to start off with, who am I? Nicely introduced already, Thomas Rooijakkers. I'm a cybersecurity scientist working on security by design principles, techniques like fuzzing, and a big fan of DevSecOps, or in my opinion, SecDevOps, as security should come first. I live somewhere in the middle of the Netherlands, and as I mentioned, I work for a company, TNO, a research institute in the Netherlands, as a senior scientist. So you might wonder, what is this TNO? We are the largest research institute in the Netherlands, focusing on a lot of different topics, almost any topic you can think of, but also cybersecurity. We are instituted by the Dutch government, by law actually, about 5,000 colleagues, and we're not for profit. Our main goal is to bridge the gap between industry and academia, so try to bring actual academic works to practice, and thereby create an impact for the Dutch society, but also the broader society. And for those who don't know, the Netherlands is at the red pinpoint. All right. Let's get started. So today I want to talk about fuzzing, specifically REST API fuzzing, but let's start with the key principles of fuzzing. So for those who don't know, fuzzing is a dynamic software testing technique in which you try to trigger unexpected behavior or undefined behavior in an application by sending semi-random input or seemingly random inputs to the application. So you could, in an analogy, see this as a child or maybe your niece or nephew grabbing your phone, trying to send all kinds of instructions, and somehow they either break your phone or they manage to get in somehow. You don't really understand why. Well, a fuzzer follows a similar principle. It's driven by trying a lot of random stuff, so you want a high volume of inputs to be sent to your application. The nice benefit you get is you decrease your testing bias. As a developer, it's very easy to write tests that follow a certain happy flow. You might think of some tests that also follow the not so happy flow, but it's quite hard to test the things you don't expect for the simple reason that you don't expect them. A fuzzer doesn't take this into account, so they also test the unexpected, and they can be fully automated, which is also a very nice aspect. I would say conceptually, fuzzing is very simple. It's rather complex to do it in practice, which we'll also see in the rest of the presentation. So as an example, I've made an image here of Mario, Super Mario. Many of you will know him. We fed this image to a fuzzer that was actually testing image parsing library. And I just want to demonstrate some of the mutations this fuzzer is generating and feeding to the library to test whether it's functioning correctly. Before diving deeper into the challenges with fuzzing, I first want to dive a bit deeper into when and where you want to apply fuzzing, and also mention some common misconceptions. So fuzzing is a technique similar to stress testing, is what some people might think. This is not true. So fuzzing is indeed also a technique where you send a lot of inputs to your application to test whether it responds properly. But the goal is not to overload your application and DOS the application, but rather you want to see whether there's some weird behavior triggered by certain inputs. So stress testing can be a side effect, but not your main goal. It's also not used to attack a system. So fuzzing can be a nice tool in your toolset as a hacker to find issues with an application you're testing, but you will not attack a live system for the simple reason that you will be noticed probably, and there are many mitigation plays to prevent you to send a lot of inputs to an application you're testing. Rather, the results of a fuzzing campaign that you run locally can be used to build an exploit, for instance, or of course to patch your system in the better case. It's therefore also not only valuable to pen testing, but it's also very valuable for developers to apply fuzzing and strengthen the application. And it's also not only used for security testing. It originates from security testing, I would say, but it also helps in improving the reliability in general of the application, because many things are unhandled, might not be exploitable, but still hinder the reliability of your application. So when can you do this? Well, of course, during development. Actually, in any stage you can apply fuzz testing to generate tests. I would say the more complex your tests get, the more interesting it is to apply fuzzing. You can, of course, do it just before releasing, in your acceptance testing or during penetration testing, but also to test the dependencies you're using. And after you release your software, it's always wise to keep testing your application to see whether you can find bugs and vulnerabilities in your software. So why are we focusing on fuzz testing? Well, as already briefly mentioned, we want to improve the reliability of our application and the security of the application by trying all kind of random or semi-random stuff. A nice aspect of fuzzing is that the results are repeatable and you actually do have a payload. Since it's a dynamic testing technique, you're testing your application runtime, and the results you find are actual issues with your application, as opposed to many static analysis tools that will find a lot of false positives. Also, if you have the issues at hand, you can also use them in regression testing. And the nice part here is that once you manage to set it up, it can be quite a challenge to set it up. It's rather cheap to keep testing and continue your testing. Very important here is that fuzzers are not workers, so they can just run in the background 24/7. They don't go to sleep and stuff like that. Some trade-offs. Fuzzing can be considered somewhat of an art. There are many aspects, also depending on the context and the application you want to test, which you need to take into account. I already mentioned performance is a key driver, so you want to try many different things. But if you do some intelligent stuff, that might actually decrease the amount of inputs you can send to your application, but still you might be able to get deeper into the logic you're testing. There's some structured approach. You can be very structured, but then you get close to the happy flow of the developer. If you're very unstructured, you're testing or scratching the surface maybe. Then there's also an aspect of feedback that you can use. So how much feedback do you want to use to guide your fuzzer in the right direction? So many different fuzzers exist out in the open, also in the open source world, and they all have their specific purpose. I wouldn't say one is better than the other, but it depends on your context. So some are very performant, use some structure, but are not that intelligent in generating new inputs that they are going to send. Then you have others that are way more intelligent, use a lot of feedback, but that comes at a cost, so the performance is decreased a bit. Then you have some more black box like approaches that use some structure, quite some structure actually, and are very important for performance, so really focus on sending as much as they can. And then you also have these very intelligent fuzzers that use all kind of nice white box approaches, use a lot of feedback, but are rather unperformant in the number of inputs they send. Then we get to fuzzing REST APIs. So, yeah. For the business people, well, an API is a common attack surface, often exposed, also publicly. Well, you want to enhance your trust and reduce the risks of your API, and thereby improve the security posture of the company. And it's, of course, handling a lot of input, so it's something you want to protect. For the techies, you want to uncover hidden bugs, so the things you didn't think of yourself. It can be automated, which is always nice. And it complements also the other testing techniques and methods that you're using. So it's definitely not a replacement. So today, we're presenting WuppieFuzz, released actually last year already, but are now going to be more publicly present. You can download it for free on GitHub and use it in whatever way you want. It's an Apache 2.0 license, so feel free to use it. The goal of presenting this to you is to advance the science around REST API fuzzing, but also bridging this gap to industry. There are some key challenges in fuzzing REST APIs. So you need some structure in sending input to your API, as opposed to binary fuzzing where you can send random bytes to your application you're testing. In REST APIs, that doesn't work, simply because, well, you need to parse the HTTP layer, you need to pass the specific requirements and the spec. There is also a notion of state in APIs, so requests have relation to each other, and input might be reused. And you might want to think about how can you make it more intelligent and guide your fuzzer actually to go deeper into the application and the business logic you're testing. So for the first one, the structured input that's required, we build a so-called harness with our fuzzer that helps you to send inputs to your application that follow the HTTP standard and also the REST standardization. For the notion of state, we can consider using things like the CRUD, create, read, update, delete methodology. And in intelligent runtime instrumentation, we look at can we use code coverage, for instance, as a metric to enhance the fuzzer. If we look at fuzzing REST API, so for the first challenge, well, there's a lot of communication ongoing between application and backends, the front ends and backends. There is a spec available, which we can nicely utilize. Well, the spec leads to code, and there is some persistent storage. If we combine all these things, we can send this malformed Mario to a REST API in such a way that it's actually covering actual code and not just scratching the HTTP parsing layer or the REST layer. Another challenge you might have is that, well, in APIs, you might send a malformed Mario and not trigger a bug. Then you send a proper input, a proper Mario, and this triggers a bug, which is actually weird, because if you would send this proper Mario in the first place, it wouldn't trigger a bug. So there is some notion of state, and you need to take that into account. How we do that? Well, we follow this CRUD concept, and we create sequences of requests as the things our fuzzer is mutating, and also reuse, for instance, identifiers that are returned by a create, in this case, a cat endpoint. You get a pet identifier back, which you can then use to create, for instance, an order. That's all great. This is what it looks like in the command line. If you consider this nice happy flow, and you follow the happy flow, what would happen if you would mutate the order and the sequence of requests that you're sending? Let's say you would delete the cat before actually finishing the order. What would happen if you would then try to still well, update the cat or update the order with a missing cat? Ideally, of course, this wouldn't trigger a bug, but in practice, often this is not considered. It is also something our fuzzer is testing. Then to the third challenge, let's first look at what a fuzzing campaign generally looks like. So we do an attack surface analysis. We try to identify where we can actually feed data to our application we're testing. In this case, that would be the REST API, so that's rather easy. Then the fuzzer is generating input, executing this input in the application. Then we're observing what happens, trying to see whether we triggered bugs or other issues. And then use this information, for instance, as a form of feedback to generate new inputs in the following stages. If we find crashing inputs or bugs, we can triage those crashes and, well, do follow-up steps like exploiting or patching the issue at hand. So how can we make it smarter? Well, we can use something called coverage. We can use this coverage to guide the fuzzer into what kind of inputs are an interesting starting point to further mutate. Well, we can look at more the black box approach, I would say. We just look at the API and see what the responses are and use that information to guide the fuzzer. And then there's also something in between where we do have a binary that we can instrument to get binary coverage information, or we might even have the source code and do more deeper inspection of the code. If you go right from left, well, the nice part is you need less knowledge. It's also way easier to set up in a black box manner than if you're testing white box. If you go left to right, well, there's more information available that you can actually use to enhance your fuzzer, enhance the mutations that the fuzzer generates, and try to get deeper into your business logic and trigger those more complex bugs that you're after. In WuppieFuzz, we support all these modes actually. So there's a minimal approach in a black box sense where we just look at the API spec and we try to have the combination of method, path, and response code, and use that as a coverage metric, so it still provides actually quite some information as opposed to many other black box approaches, and use that to guide our fuzzer in mutating more intelligently. But if you want to do it a bit more extensive, you can also attach a coverage agent to your API, so that's running next to your API, and it actually tracks coverage of the input that the fuzzer is sending. It communicates with a coverage client that's actually present in the fuzzer, in WuppieFuzz, and WuppieFuzz is using this information, this coverage information, to get deeper into your code. As an example, we support a set of languages, specifically Java. For Java, we use the standardized Jacoco Java code coverage library, which you can easily attach with a single argument in your command line. So what can WuppieFuzz do? Well, it can help find vulnerable points and other issues in your code base. There are many symptoms to look for. Well, the rather trivial one is the 5xx codes. Those are codes that are related to internal server errors. So those are things that the developer didn't think of, or are either not handled by the application sufficiently. But it also checks, according to the spec, whether the responses are actually in line with what the developer and the designers of the application or the API were thinking. So if there are any mismatches, those are reported. For instance, there could be extra fields in the reply. You might leak information because the responses somehow give more information than the specification is specifying. And other things you can also do, where there's also a nice Grafana dashboard available, so you can further explore all the requests that were sent and also see whether there could be some information leaks in terms of authorization. For instance, examples are like GitHub. If you're not logged in properly or don't have the authorization to view a certain repository, you will get a 404 not found. If you would get a 401 unauthorized, you would know that actually this repository exists. So that's something you might want to prevent. So those kind of issues can also be spotted using the dashboard. And I think that brings me to the last slide. So once again, well, feel free to scan this QR code. If you don't trust QR codes, there's also this TNO.2 address that you can use, which redirects to GitHub. If you don't trust TNO.2, I can also imagine that. Just go to GitHub and go to TNO as /WuppieFuzz, and you'll find my repo there. Thanks.